Today, today's topic is IoT, application of IoT. That is domain-specific IoT in industry. So the core concepts, what is industrial IoT? Like IIoT. Industrial IoT refers to the use of interconnected sensors, instruments, and other devices in industrial applications like manufacturing, energy, and logistics. It is the backbone of the fourth industrial revolution, Industry 4.0. And we can see the key differentiators from consumer IoT or scale and criticality manages heavy machinery and complex processes where failure is costly and dangerous. Precision and latency requires extreme high reliability and real-time or near real-time responses. Environment operates in harsh conditions, temperature, vibration, EMI, and lifespan. Industrial assets have lifespans of 10 to 20 years, demanding backward compatibility and long-term support. And the IoT architecture, in this perspective of our computer science major, it is like those are all listed in the following. Extensive standard IoT architecture with a strong focus on integration, data, and security, which we will be more into. Edge or device layers like sensors, actuators, PLCs. PLC is nothing but programmable logic controller. And the industrial applications and examples like sensors, vibration, temperature, pressure, flow, proximity, vision system, actuators, robotic arms, motor drives, solenoid, valves, PLCs, the old god of industrial control, now being integrated with IIoT. Connectivity layer, industrial communication protocols, field bus protocols, Modbus, Profibus, legacy still widely used, Ethernet-based OPC UA open platform communication, unified architecture, the modern standard for semantic interoperability. And wireless technologies used by the devices are like 5G, URLLC, ultra reliable low latency communication for mobile robotics and AGVs. And data processing layer like edge or edge gateways and cloud platforms like edge computing for real-time control, anomaly detection, and data pre-processing to reduce latency and bandwidth. Cloud on-prem for massive data aggregation, historical analysis, and running complex ML models. And application and analytics layer, software, dashboards, AAML. SCADA, that is supervisory control and data acquisition for monitoring and control. MES, manufacturing execution systems for tracking production. Digital twins, a virtual model of a physical assets or process for simulation and analysis. Security layer, cross-cutting security, zero trust architecture, device authentication, encrypted communication, access controls applied at every layer, and key IIoT applications and system design. Use case one, predictive maintenance. Problems like unplanned downtime of a critical machine like a compressor is exactly extremely costly. And IoT solutions, sensing vibration and acoustic sensors are mounted on the compressors, bearings, and motor. Communication data is streamed via an OPC UA servers to an edge gateway. Processing edge, the gateways runs a lightweight ML models to analyze the vibration spectrum in real time. If it detects a signature of an early bearing wear, it sends an alert. Processing cloud, all vibration data is stored in the cloud. A more complex model correlates this data with historical failure records to predict the remaining useful life RUL of the components. Applications or like these kind. these used in the maintenance team receives an alert on their dashboard to schedule repairs during the next planned shutdown, avoiding catastrophic failures. Use case 2 or like smart logistics and asset tracking. In this, you can see the problem is inefficient tracking of materials and assets within a large factory or supply chain. IIoT solution, sensing AGVs, automated guided vehicles, and components are tagged with GPS, RFIDs, or UWB, ultra wideband tags. And communication, 5G or Wi-Fi 6 provides seamless high bandwidth connectivity across the facility. Processing cloud, a central logistic software platform, tracks the real-time location of all assets. And applications and analytics. The system optimizes routes for AGVs, provides real-time inventory visibility, and triggering automatic reordering when stock is low. The role of digital twins. This is a critical concept of emphasis for CAC students. A digital twin is a dynamic virtual representation of a physical asset or system. How it works is IoT sensors provide a continuous stream of data from the physical asset to its digital twin. CAC value like twin can be used to simulate, test what if say, scenarios. Example, what happens if we run the machine at 10% faster, predict use data and ML to forecast failures, optimize, find the most efficient operating parameters in the virtual mode, and then apply them to the physical mode. So, in class activities, you can do these things like designing an IIoT solution for quality controls. Scenario, you can take a scenario like an automotive assembly line has a problem with misaligned windshield installations. This is only caught at the final inspection station, leading to expensive rework. A task in groups, students must design an IIoT system for early detection. Deliverable, a brief architectural diagram and explanation covering sensing what sensors would you use and where. Example, a vision system camera at the windshield installation station. Communication, how would you get the data to a processor? Example, gigabit Ethernet for high-speed image transfer. Processing, where would the analysis happen? Edge to cloud, and what would it do? Example, edge processing using a lightweight CNN model to analyze the image in real time and check for misalignment. Action, what is the output? Example, immediately alert the operator on their HMI, human machine interface, and halt the assembly line if a fault is detected. And further reading and project ideas like you can try with these things. So that's all about domain specific IoT, that is industry. Thanks for joining.